In thermal physics this year, we will talk a lot about gases. Gases consist of a relatively dilute bunch of atoms or molecules which are not bound to each other. Instead, they're free to roam, they zip through space at great speed, colliding with each other every now and colliding with walls when they encounter one, or any objects for that matter. In a gas, only about 1/1000th of the space is filled with molecule. The rest is just empty. Or in other words, if you were to closely pack all the molecules present in 1 liter of air, which is the volume of this pack of long life milk, which I totally did not panic buy at the beginning of the pandemic craze, you'd fill only 1 milliliter, or the volume of a stock cube. So this volume of gas contains only that much molecules. The rest is empty space. So the molecules in this gas bounce around at great speed. How fast we'll discuss a bit later in this course. Their motion is random. The direction of their velocity is random. So on average, the gas doesn't move. Only within the gas, the molecules just go in all directions. However, each molecule has a velocity in the reference frame of the container. And so it has kinetic energy and it has momentum. Whenever a molecule hits a wall, it bounces off the wall in a collision that we can safely assume to be elastic. The wall is much heavier than the molecule, which is a very similar situation to what you saw in mechanics when looking at the bouncing of the ball from the ground. Remember, the ball falls and bounces back up again, with basically the velocity vector just inverted. That was derived, in fact, from conservation of energy and from momentum. You can work out that the velocity of the molecule after the collision is simply flipped. The velocity remains the same, but away from the wall. The velocity vector parallel to the wall remains the same. The direction perpendicular to the wall is just flipped. So there's a change of momentum, which is perpendicular to the wall. That change of momentum requires a force. That force is a force from the wall on the molecule, which changes the momentum of the molecule. And by Newton's third law, there's also a force of the molecule on the wall. So the molecules, during the collision, exert a force onto the wall. And that force is perpendicular to the wall because the momentum change is only perpendicular to the wall. In simple terms, whenever a molecule hits the wall, it pushes it a little. So if the wall had a finite mass, for example, and is mobile, it's not attached to anything, then the wall would start moving because F equals ma. If there's a force and a finite mass, then there is some acceleration. That acceleration would be in the same direction of the force, and that is perpendicular to the wall, like in this animation. So the gas exerts a force on the wall in a direction perpendicular to the wall. That force is proportional to the number of molecules hitting the wall, which, assuming the molecule's density is uniform, is proportional to the surface area of the wall itself. So on this animation, we have two different walls. On the top, we have a small wall, and on the bottom, a larger wall with a larger surface area. But both walls have the same mass. The bigger wall is accelerating twice as fast, clearly showing that the force is double. Note, the wall doesn't need to contain the gas. Any object immersed in the gas also experiences a force on each surface. If there's no internal force to keep the shape of the object, it would just collapse. Gases exert a force on walls that is perpendicular to the wall, with magnitude proportional to the surface area of the wall. If you have a wall with surface area A, with a gas on this side, it will exert a force F in this direction. The force is proportional to the surface area, and what we define to be the pressure, it's not a vector, the pressure is simply the magnitude of the force divided by the surface area. That is called the pressure, denoted lower P. Pressure is a property of the gas itself. From it you can calculate the force on any wall the gas encounters, whatever that wall may be made of or in which orientation it may be. The force on a wall is then simply F is equal to the pressure P lowercase p, times the surface area, times a normal vector to the surface. The unit vector that is orthogonal to the wall. The unit of pressure is thus Newton per square meter, which is such a common quantity that it's got its own name, the Pascal, named after French mathematician, physicist, and philosopher Blaise Pascal. So 1 Pascal is equal to 1 Newton per square meter, and the pressure is in Pascal. It's called a Pascal, spelled like this. If you have a surface of 1 square meter with a gas at a pressure of 1 Pascal, the gas will exert a force of 1 Newton on that wall. That, as it turns out, is a very small unit. The atmosphere has a pressure of around 100,000 pascals, so there's a couple of units for that too. More convenient units for the atmosphere, for example, the bar. 1 bar is equal to 10 to the 5 pascals, and also the atmosphere, or the standard atmosphere, which is 101,325 pascals. Another unit that is frequently used is a hectopascal. 1 hectopascal is equal to 100 pascal, and of course the kilopascal, which is just 1,000 pascals. All right, let's look at an example. In a plane flying at 10,000 meters altitude, the outside pressure is 30 kilopascals at that altitude. The inside pressure in a pressurized plane is stabilized at around 78.2 kilopascals, which is roughly the pressure that you get at about 2,000 meters at altitude, which is a relatively comfortable pressure for humans without much adaptation. Each window has a surface area of about 0.12 square meters. What is the net force due to the gases inside and out on the window? Well, we have a window, we have the pressure outside, we have the pressure inside. The pressure outside causes a force pointing inwards, and the pressure inside causes a force pointing outwards. So if we give ourselves a unit vector x in that direction, we have that the forces along x are FO, the total net force F net is equal to F naught minus Fi along x, the force due to the gases outside minus the forces due to the gases inside, and that is simply then the pressure outside multiplied by the surface area minus the pressure inside multiplied by the surface area. And if we plug in numbers to that, we get that the force is equal to 5.8 kilonewtons. That's the same force as exerted by about 580 kilograms of weight at ground level. So that's quite a very high pressure on each window. So forces due to pressures tend to be large numbers. That's something good to remember. Now, the concept of pressure doesn't just apply to gases, but also to liquids. For solids, it becomes a bit more complicated, as forces can then depend on the direction. And instead of having a single number expressing the force per unit area, we need to use what is called a stress tensor, which is a bit like a matrix, but we won't do that this year or even next. You'll see that in third-year physics. So to summarize, pressure is due to molecules colliding against walls. The pressure expresses the force per unit area on any wall or object in the gas, and its unit is the Pascal, which is 1 Newton per square meter. Now that you know all about pressure, in the first lecture coming on Monday, we will discuss what temperature is, which is a much more subtle concept, in fact. Perhaps start to think about how you would define temperature. Until then, cheerio.